Hi, what is a brushed DC motor? It's a motor that runs on DC voltage. How to drive it? You just stick it to a DC voltage. Hey, calm your shaft. I said calm your shaft. Why do you have to keep? It exists everywhere, from your hair dryer. Yes, it's a DC motor. They pass the AC through the heater element to drop the voltage and then pass it through a full bridge rectifier to give it to the motor. They exist in cordless drills, although some drills have brushless DC motors, but that's another story. And they exist in fans and toys and drones and vibrators of your mobile phones. Let's make a simple one. First, I want to make the stator, the stationary part of the motor, out of these plastic old CD covers. I just cut some walls out of it. Then we glue the walls together. There, a tiny little stator box. Then we need two permanent magnets with north on one side and south on the other side. Then we just glue the magnet north in on one side and south in on the other side, like this. Then we just poke two holes right between the magnets on the walls. Now to make the rotor, the part of the motor that rotates, we take a nail and cut the end off. Then we take some steel wire and twist it around the nail to shape a cross. Something like this, a little bit off center and the same length on both sides. Now we get some magnet wire, which is basically coated copper wire, and we can get this from old wall adapters and wrap it always in the same direction around the steel wire. So we make something like this. Then we remove the coating from the end of the wires. Then we place the nail in the holes of our stator. Now you see, if I pass electricity through the coil, it tries to realign itself. If I can grab it. Come on. It keeps shaking. Okay. See, it tries to realign itself with the magnetic fields and rotate. Now we put some electric tape on the nail to isolate it. Move the wires to a location perpendicular to the coil and cut the extra pieces and remove their coating. Now we need to make something called a commutator, which is just contacts to these wires and brushes that will touch them. I made my rotor too small. Maybe you want to make yours a little bit larger so it's easier to work with. For the contacts, I need something rugged, so I'm gonna cut the metal off of this food can. I have to sand the surface to expose the conductive metal. I can even solder my wires to them. There you go. Not bad, eh? Okay, the moment of truth. I'm connecting my power supply using these wires as brushes over my commutator. Let's see if it turns. There you go! Success! See how much arcs are flying off of the commutator. The amount of heat and current is damaging my contacts and glues. I should have made it better. But the commutator and brushes are the downside of brushed DC motors. This is an actual rotor I took from a small motor and can work in the same setup. There we go. Now what do you know? It's designed much better than my rotor. They don't make two-pole rotors anyway, it's always 3 and above. Now there are tons of different motor designs and you have to pick one for your application. Choosing proper torque depending on your load. You need to use gears to increase your select what RPM the motor should run. You need to study torque and speed plots. You're limited by the space and weight in your design. Nominal and maximum voltage and current is typically stronger turning one way than the other. What I'm trying to say is that there are a bunch of mechanical considerations to pick a proper motor, and you let your mechanical engineer minions to take care of those low-level stuff. We are here to drive it. Now there are a bunch of challenges driving any motor, which is typically at startup and shutdown and during the operation. So let's see what they are. But a lot of what I'll say applies to all electric motors. The brushes and contacts of a motor, which is called the commutator, is an interesting arrangement. If you think about it, it converts the DC input to AC over the coil, because as the rotor turns, it flips the polarity over the coil. If we turn the motor manually, we generate electricity simply because we are moving the rotor coils through magnetic fields. This generates AC over the coils, say around 100 Hz, but the commutator rectifies it at the input. And if you look closely, you will see that I have a brand new 4-channel Keysight scope. They just came up with this scope. This is the new brother of, or sister, I'm not sure, I don't want to assume its gender. The new model of my 2-channel scope. It has all the great features of my beloved scope, comes in Batman Black, 4-channel, 200 MHz, and I'll give away 4 of these at the end of the video. You can sign up from the link in the description, which also puts you in Keysight's Wave 2019 equipment giveaway, which happens in March. More detail at the end. Now I'm going to spit out a ton of information around DC motor drive. It is guaranteed to hurt your brain, so save yourselves or buckle up. So a motor with permanent magnets acts as a generator too, outputting a bumpy voltage. But even when we run it from a power supply, the generation action still happens and creates electromotive force or voltage that comes back from the motor, that we call back EMF. A simplified model of the motor winding looks like this. The inductance of the winding in series with the resistance of the wires in series with an AC source for back EMF. This regenerative voltage source exists on all the windings of the rotor, and its voltage is dependent on the speed of the motor, starting from 0 when the motor is not turning and goes up by speed, all the way close to the supply voltage. The back EMF sources of different windings get rectified through the commutator, similar to a 3-phase, even fuller bridge rectifier, and create a bumpy DC source. So you can model the DC motor at the supply lines like this. The inductance of the winding series with the total resistance of the motor series with a rough DC voltage supply. Now here's the interesting part. For a well-made and lubricated motor, we expect a small input current when no load is attached to the motor. It is because when we start the motor and it speeds up, the back EMF voltage rises close to the supply voltage, creating a small voltage drop across the motor resistance, which means small current draw. The winding inductance is short circuit for DC. But as you load the motor, it slows down, and so the back EMF voltage drops, causing a higher voltage across resistance or higher current draw. The higher current results in a stronger magnetic field, and so the motor turns with a stronger torque to keep up with the load. This is why if the motor ceases to rotate, it can burn, because the back EMF drops to 0 and the entire supply voltage falls across the resistor. Knowing all these, let's start a motor using a battery and measure the current on the scope. See, the current spikes to around 80 amps even for this tiny motor, and then drops to around 3 amps. It is because at the beginning there is no back EMF to lower the current, and the current drops as the back EMF rises with the rise of the motor speed. They call this initial spike the inrush current. Motors like engine starters draw over 200 amps of inrush. We had a motor at work that would draw over 800 amps of inrush. This imposes a huge startup challenge for systems that can't handle this much current. You might say the motor has a series inductor that should limit the current. No! The electrical time constant, being L over R, is very small, in milliseconds, much smaller than the mechanical time constant. So the current jumps to maximum, which is the supply voltage divided by resistance, very quickly, around 2 milliseconds here, before the motor has time to speed up and lower the current over 100 milliseconds here. Now let's turn off the motor and look at its voltage. Look at that. I turn off the motor around here, then it's kind of flat for around 6 microseconds, then there's a huge negative spike of over 100 volts. The reason it's flat at the beginning is that when I disconnect the wires, there is a tiny arc between them for a few microseconds that limits the motor voltage. But as soon as the arc goes away, bam, there's a huge voltage spike. When we discharge an inductive load like a motor, the inductance energy discharges, creating a large negative voltage spike that can create an arc across the contacts. This arc momentarily shorts the discharge energy. This initially limits the voltage across the motor, but when the arc goes away, the voltage jumps to minus 100 volts as we saw. If there was no arc, the voltage would jump thousands of volts. Without protection, any circuit would blow up. This is one of the main reasons that the commutator brushes get burned and wear away, the main downside of brushed DC motors. Because when those brushes switch around, there will be high temperature arcs between the contacts that wear them away. If we look at the shutdown voltage again over a longer period, you see after the negative inductive spike, the voltage returns positive and declines slowly. This is the back EMF at work. The motor hasn't stopped yet as it has momentum. The fuzzy noise is due to commutator switching. So the back EMF voltage goes down as the motor stops. This can cause us trouble later, or we can suck the back EMF energy out and use it, which would result in the motor stopping faster. That's called regenerative braking. Now I'm running the motor from my power supply, measuring the current. And if I short the contacts, see, it draws around 70 amps from the motor, sucking the back EMF energy and stopping the motor quickly. Okay, so there are problems driving motors. Let's calm down and try to solve them. First, the high voltage spike at shutdown. It's a simple one. As a good solution, we can just add a reverse diode across the motor. This diode is called a flyback or freewheeling diode. When we run the motor, the diode is off. But when we disconnect the motor and the voltage of the motor flips, the diode turns on and the current loops through the diode for the short time constant of the inductor. So the reverse voltage across the motor will be limited to the diode voltage, around -1 volt. And after the inductive energy goes away, the back EMF kicks in. Vroom! Let's try it. I put a diode across the motor contacts, and if I turn it on... Ooh, my diode blew up. It was in reverse. So in this method, we can only run the motor in one direction. Trying again, I turn it off, and you see the voltage only goes negative a little bit. There are no arcs, and the voltage rises back up due to back EMF. Okay, one problem solved. Now how do we help the large startup inrush current? One good solution would be to raise the supply voltage slowly to have a limited current while the motor ramps up. And that's exactly what we do. We limit the supply applied to the motor using PWM or pulse width modulation. Imagine we have a switch and we turn it on and off quickly at a fixed frequency. Initially, we give it a short on time so the motor has time to ramp up, and we increase the on time until it reaches the maximum speed. The switches we use in our circuits are fast N-channel MOSFET transistors because they have a very small on resistance and waste little power. I'm not going to talk about MOSFETs and how to drive them properly. That's a whole other topic. If we turn on the motor straight up, the inrush current rises to maximum with a time constant of L over R, then drops slowly as the motor ramps up. First off, your initial PWM on time should be shorter than this rise time, which is in milliseconds. Otherwise, the current reaches maximum and it defeats the purpose. Now, picking up the PWM frequency is important. For best control, the PWM period should be shorter than this inductive rise or fall time. Say, smaller than 3 time constants. And that's me talking from experience. It might be written somewhere more formally. Let me explain. Imagine the motor is running and we have this voltage across it. Then we turn it off. We have the negative inductive kick clamped by the diode and then the back EMF. If the PWM goes on during the back EMF, we are letting some of the back EMF during the off time. Then the voltage goes back up and the cycle continues. This means that the motor current drops to 0 every cycle. This results in an unpredictable voltage across the motor because this regeneration voltage depends on speed and RPM and things. So for better control, we pick a higher frequency to keep this voltage out. This way, the motor voltage would be nice and square, with its average equal to the duty cycle times the supply voltage. And the motor current would be a nice ripply DC equal to the supply current average divided by the duty cycle. Here I have a MOSFET transistor series with my motor, and I'm driving its gate from my function generator, and I'm measuring the motor voltage and PWM input. I'm running the PWM at 50%, and you see if I change the frequency, it doesn't affect the speed of the motor until I lower it so far that the regeneration voltage gets into the off time. You see the motor is running faster with the same PWM. This additional back EMF voltage is raising the average voltage across the motor, which also changes by load and speed. That's why we keep the frequency higher to keep the voltage across the motor constant for better control. Now you see, changing the PWM can nicely change the speed. And this is how we manage the inrush current by controlling the motor supply. Instead of turning the motor dead on, we PWM it on and off and control the current until it hits the curve we want. We can control it to completely remove the inrush or allow some acceptable inrush to get in. If we raise the current slowly, the motor ramps up slowly. So in some application that we need a more responsive motor, we allow some inrush current so that the motor can kick on faster. Now let me show you some current plots. The motor draws current from the supply in the on time and loops the current through the diode in the off time. So the supply current is the same as the motor in the on time and 0 in the off time, which is the same as the transistor current. And the diode current is 0 in the on time and the same as the motor current in the off time. Now this is important. We have to pick our components so that they can handle this current. Also, you see that we are switching large currents through the supply and diode, so the electromagnetic radiations become an issue. Filtering for those is a whole other issue I won't discuss here. Are you tired yet? But wait, there's more! So far we have been driving the motor through a puny single transistor. It's time for a half-bridge driver. See, running the current through the diode wastes some good power. So if instead we replace it with a low on resistance transistor, we could save much more power. Like with this toggle switch, I can switch it on and off. Damn it. I guess I can't switch it at kilohertz frequency. Remember when switching the motor voltage with a flyback diode, at low frequency PWM, the back EMF voltage would get in during the off time because the diode would turn off. But if we replace the diode with a switch like I did or a MOSFET, it won't turn off, shorting the back EMF voltage and breaking the motor. So this is important. When using a half bridge, the PWM frequency must be fast, faster than the inductive discharge time. Otherwise you will stop the motor every cycle. Now let me turn on the motor using my half bridge. If I can turn on the PWM, well, clearly at the moment I don't have the means to drive the half bridge. An important thing running a half bridge is that the two switches must never turn on at the same time. Otherwise they'll short the power supply, a huge current will shoot through them and they'll blow up. The control signals must be such that one transistor turns off before the other one turns on, and for safety we keep a time gap between them called the dead time, during which both transistors are off. For better control though, we want dead time to be as short as safely possible. You might ask, if both transistors are off at the same time, then what will absorb that high voltage inductive kick? Well, the good thing about MOSFETs is that they naturally have these internal diodes that do the job. So let's see what happens when we PWM the motor. The motor can connect to the ground or positive, doesn't make a difference in control. First, the top FET is on and the current flows through the motor and the motor voltage is positive. Then the top FET turns off and the motor current runs through the body diode of the lower FET, and the motor voltage drops below ground for the short period of dead time until the low FET turns on and the current runs through it. Then the low FET turns off and the current runs through the body diode again until we turn the top FET on. This is what you see if you probe the motor voltage. So at startup, we ramp up the PWM duty cycle to limit the inrush current, and at power down, we can just turn off the switches and let the motor stop on its own or ramp down the duty cycle. If we ramp down the duty cycle faster than the natural motor slowdown rate, this act will suck the back EMF energy from the motor and force it to slow down faster by pumping current back into the power supply. You can use this current to charge a battery, as in regenerative braking. But if you don't have a battery or supply to absorb this current, it will push your supply voltage high, probably too high, and kills all your circuits. This has happened before. The easiest solution in this case is to turn off all the switches when a high voltage is detected and stop pumping the current. I think we took care of everything. But no! So using a half bridge, you can change the duty cycle to change the energy input to the motor and control the speed, but not the direction. That's why we put two half bridge drivers together to make a full bridge driver, which they also call an H bridge because it looks like an H. There are 4 switches and the motor connects between the two halves. If you turn these 2 switches on, the motor turns one way, and if you turn these 2 on, the motor turns the other way. There are different ways to drive an H bridge, but for example, we can turn this off and that on continuously and PWM these 2 for one direction, or turn this off and that on continuously and PWM this one for the opposite direction. I think we successfully scratched the surface of how to drive brushless DC motors. There's not much left. The rest would be how to choose transistors properly, to drive the switches properly, features to expect from a driver, to design and filter for EMI, to design the PCB layout.
Giveaway time!
So thanks to Keysight, I'll give away 2 of these new babies to my patrons at patreon.com and another 2 to the viewers who can register for free from the link in the description. That link also automatically puts you in the Keysight Wave 2019 giveaway. They are giving away over $350,000 worth of test gear to over 100 people from March 1st to 15th. Super scopes, meters, function generators. You get an early entry up to February 28th straight from my link and 1 entry per day during the March period signing up at wavekeysight.com. Also 2 schools from December and 1 from January win scopes and tools from Turkey, India and US. Thanks to Keysight and the support of my patrons to support education.